Okay, the next chapter we'll cover is chapter 7. And this chapter deals with quantum mechanics, sort of as they relate to the atom. And we'll talk about light and energy and sort of how those things are kind of changeable in certain ways, and about some of their properties. This is kind of an interesting chapter, I think, in that sort of the topic is very interesting. The math will be much lighter for you. Very simple equations, at least for just this brief sort of overview that we'll do. When you get into deeper quantum mechanics, the math gets pretty challenging. But the concepts here will be a lot heavier, I think, than something we've done so far. But like I said, the math will be a little more relaxed. And I think this is kind of a cool chapter in that if you tell your friends or your family you're studying quantum mechanics, they'll probably get a kick out of it. Okay, so let's dig into it. So the first thing we'll talk about is this dual nature, so to speak. Okay, so we'll start with a quote from Heisenberg, and he says, "Light and matter are both single entities, and the apparent duality arises in the limitations of our language." Okay, so what he's saying here is that there's a lot of shared properties between matter and light. It's just sort of the way we describe it that gives it sort of a different nature. Okay, so we'll start by just going over this dual nature a little bit. Okay, so the first thing it says, matter has both particulate and energy-like behaviors. Okay, so particulate meaning that it has mass and it occupies space. And remember that matter is essentially stuff. Okay, so stuff we know has mass and occupies stuff, or space, excuse me. But it also has wave-like behaviors or energy-like behaviors. Okay, and we'll hopefully understand this as we go through more and more. Okay, the next thing it says, most subatomic particles, such as an electron, behave as a particle and obey the physics of light waves. Okay, and that has a lot to do with their size. Okay, so kind of what that's trying to say is that if you study electrons very closely, you'll see that it has particle behavior, of course. So we know that, and we sort of think of electrons as being these solid things, sort of, almost spheres kind of in our minds. But it also has wave-like nature, and it becomes kind of apparent because of their size. So the smaller something is, the more likely it is to inhibit both of these type of behaviors. And we call this dual personality. So all matter possesses this dual personality, whether it's light, matter, electrons, all this stuff, all has this dual personality. Okay, and we call this the wave duality. Okay, and so the theory that describes all of this and sort of puts it all into one house is quantum mechanics. And that's what this chapter will mainly be over. Okay, so hopefully this sort of sets up some interesting ideas that we'll get into. So first we'll just start with some definitions and variables. So the first thing, light waves have a frequency. Okay, we'll denote frequency with a Greek letter nu. So it sort of looks like a lowercase v. This is a nu. It's like a curvy v almost. Okay, and this has units of cycles per second. In other words, 1 over seconds or seconds to the minus 1. Okay, so these two things are the same. So if you see minus 1 like this or minus 2, it means 1 over or 1 over squared, whatever it is. Okay, the distance between light waves is often referred to as wavelength. Okay, and we use lambda for this. Sort of looks like a curvy h. Okay, and we'll give it units of meters or nanometers. Two formulas, we're going to say that wavelength times towards frequency is equal to c, where c is the velocity of light in a vacuum, which is 3 times 10 to the 8th meters per second. And then we can say frequency is equal to c over lambda. Okay, so this is kind of for this class anyway, the level of the math that we'll be doing. Just sort of some simple formulas. Nothing nearly as deep as we got into in thermo. Okay, which even in thermo, we'll get much deeper into that next semester. Okay. So first, let's sort of define what wavelength is versus what frequency is. So the first thing, wavelength. So wavelength is if we choose an imaginary point on a wave. So the easiest way to do this is the crest. Okay, so from crest to crest. So I didn't know I could do that. So from point to point on a wave, the distance between those 2 points, that's your wavelength. Okay, so every wave has a wavelength. So just depending on the wave, so this a wavelength would be from here to here, or from here to here. Okay, you can also do it from, say, trough to trough if you would like, or you can pick anywhere else on the line, on the wave if you would like. But just easier to do it by some sort of landmark, so to speak. Okay, so that's your wavelength. So the difference between crest to crest, that's your wavelength essentially. Your frequency is if we were to draw an imaginary line on all these waves. So you can imagine they're moving in this direction. Okay, so every time one of the crests goes by, so every time one wavelength goes by, in other words, you would count that. And the number of times a wavelength goes by, that's the frequency. So it would, for instance, have maybe, 2 crests per second, something like that. And that's your frequency. So how often does the wave go by? That's your frequency. And so these two things are related. So if I have a longer wavelength, so the first one in the sort of pink box, that's a long wavelength. Okay? But it has a small frequency. Not a short frequency, but a small frequency. In other words, there's not very many waves that go by every second because they're long. Okay, we have a longer wavelength, so it takes longer for each one to go by. The second one in the yellow box, okay, this one has a little bit shorter wavelength. Okay, so then it would have a higher frequency. In other words, there would be more complete wavelengths that go by every second. And depending on sort of how compressed or how stretched that wave is, will change its frequency. Okay, so we can say that wavelength and frequency have an inverse relationship. In other words, we can say frequency is equal to 1 over lambda. Okay, the next thing we'll talk about amplitude. Okay, so amplitude is just how tall is the wave, okay, from our center point. Okay, so this is essentially its intensity. Okay, so if this was light, in other words, this one at the top has a smaller amplitude. Okay, so it'd probably have a smaller intensity. There's just less of it there. Okay, but you notice our wavelength is the same. Okay, our frequency is the same. The only thing different is this space and this space. Okay, so there's just less there's less wave on the one on the top. There's more wave on the one on the bottom, so it has a bigger amplitude. Okay, so those are just the parts of a wave. Okay, so already we have a simple calculation here. So we just want to convert between wavelength and frequency. Okay, so it says red light has a wavelength of 700 nanometers, and we want to know what its frequency is. Okay, so give this one a try, and I'll go over it with you. Okay, so let's take a look at this. So what we want to do is we want to change nanometers to meters. Okay, so remember that there's 1 times 10 to the 9th nanometers and 1 meter, or you could say that there's 1 times 10 to the minus 9 meters per nanometer, whichever way you want to look at it. I think this is the better way to do it. Just remember that this number going from nanometers to meters should be going down. Since there's more nanometers per meter, if I go from nanometers to meter, then my number should be getting smaller. Okay, so for every 1 meter, there's 1 times 10 to the 9 nanometers. Okay, so once we've converted nanometers to meters, now we can just use our relationship. So we know that frequency, which is what we're looking for, so it asks us to just convert wavelength to frequency. And we'll say that frequency is equal to c over lambda. Plug in c, 3 times 10 to the 8th, meters per second, over 7 times 10 to the minus 7 meters. Okay, so here meters will cancel with meters. And we're left with 1 over seconds, or in other words, seconds to the minus 1. Okay, that's units of frequency. Okay, so we've at least done that part correctly. If we do our math, just divide those two together, we end up with 4.29 times 10 to the 14th, 1 over seconds. Okay, so really not too tough of a calculation, but you'll need to know how to do this sort of back and forth, because you'll be using something like this where you're given a wavelength, maybe you weren't given a frequency, in order to put this number into a second calculation, but not too bad. Okay, so just make sure you can handle going back and forth between frequency and wavelength. Okay, so this next part we'll talk about the electromagnetic spectrum, and I think this is part of the interesting topics in this chapter. So the electromagnetic spectrum illustrates the range of electromagnetic radiation. Okay, the classifications and regions of the electromagnetic radiation are based on wavelength. Okay, so we have different things. Basically what we're talking about here is we're talking about energy. Okay, and how all of this energy relates to one another. Okay, and by energy, we're talking about things like light, radio waves, gamma rays, and we'll dig into that a little bit more in just a moment. But first, let's just talk about some of the classifications. Okay, so first of all, we have things that are short wavelength. Okay, in other words, high frequency. Okay, so if we have short wavelength light, then we have a high energy wave, or we have high energy radiation. So on the other hand, we have things like radio waves that have the lowest energy, and we have gamma rays that have the highest energy. And notice here it says shortwave light, radio wave light, gamma ray light. And I'll show you exactly why that is in just a moment, but keep in mind, when we're talking about energy, we can use the word energy and light exactly interchangeable. Okay, then we have high energy electromagnetic radiation can potentially cause damage to biological molecules. In other words, this is why when you get an x-ray, you have to wear the lead gown, and the doctor, well, they don't do this anymore, but they would run behind the screen. Okay, if you're at the dentist, I know nowadays they don't do that. But keep in mind, if we have higher energy or short wavelength light, this is what causes damage to our skin, things like gamma rays. Okay, and the reason we're saying light, and the reason I say you can say light and energy interchangeably, is because visible light is just one small part of this. Okay, so visible light comprises only a small fraction of all the wavelengths on the electromagnetic spectrum. Okay, so this is what I mean. Okay, so this is our electromagnetic spectrum. In other words, it's all the types of light or all the types of energy, it's on one spectrum, and it's in terms of their wavelength or their frequency. Okay, so we can just kind of look through this, and we see things like radio waves, microwaves, infrared light, ultraviolet light, visible light, X-ray, gamma rays. So notice right here in the middle. So this little small section, that's visible light. Okay, so notice there's no other distinguishing feature about it other than its particular frequency, or in other words, its particular wavelength. It's not like it's on a separate scale or a separate category. No, it's on the same scale. Okay, so what am I telling you? So the only thing different between a radio wave, like you pick up in your car, and visible light, well, there's two main things. Well, frequency and wavelength, of course. In other words, the energy. The second distinguishing feature is that we can see it. That's it. So our eyes are detectors, just like you would find in an instrument in the laboratory. Okay, our eyes are detectors that just so happen to be able to pick up light energy from 750 nanometers to 400 nanometers. And as you start to get older, this starts to shrink in this direction. Okay? But that's the only thing special about it. Well, there's a lot of things special about visible light, but that's really it, though. So we can just happen to be able to see this part of the electromagnetic spectrum. So there's no difference, in other words, between visible light, microwaves, infrared, just the frequency and the wavelength. Okay, and as we get more towards the purple, so if we go beyond purple to ultraviolet and then X-ray and gamma, so these are higher energy. Notice they have higher frequency, so 10 to the 24th, but they also have the longest wavelengths, so much smaller wavelengths. So not longer, smaller wavelengths, but they have higher frequency. Okay, then on the other end, we have low energy. So we have radio waves, microwaves, infrared light. Okay, so these have small frequency, but long wavelengths. Okay, and broken down in radio waves, we have AM, TV, FM, and cell. Okay, so this between AM and FM. So this is why we play music on FM, because it's a little bit stronger signal compared to AM, which is usually what they put like talk radio on. Okay, so make sure you know this whole, so the scale from radio to gamma rays, and make sure you know the wavelengths of visible light, and make sure you understand the concepts we just talked about. So what exactly is color? Okay, so all electromagnetic radiation has color. Okay, however, not all electromagnetic radiation color is visible to us, to humans. Okay, so that brief part of the spectrum from 750 to 400, and you'll see those numbers slightly different depending on where you read them. This is the part that's visible to us. Like I said, simply because our eyes are good detectors for these wavelengths. Okay, so the color of light can be determined by either its wavelength or its frequency. So if you know one, you know the other. Okay, and in terms of the visible spectrum, we know that white light is a mixture of all the colors. So if you've ever played around with a prism, maybe just using a flashlight or something like that, you know that as you pass white light through the prism, it breaks into all of the colors, right? So it breaks into a rainbow. Essentially the same thing that's happening in the sky, by the way. Okay. And so in order, red, orange, yellow, green, blue, purple, or violet, just like you learned probably in kindergarten. Okay, so color happens when an object absorbs some of these wavelengths of white light and reflecting the others back. So what you see, keep in mind, so if we see something as a color, it's absorbed all of the other colors of white light, and it's bouncing that one back at our eyes. Okay, so it's like a smell. I think we talked about this in the beginning of the class. So in order to have smelled something, some of those particles of whatever's giving it that smell have to have gone into your nose. You can't smell, in other words, how can you smell something or sense something that isn't there? So it has to be something there. Well, just like with light. So what we see is actually what's reflected back at our eyes. Okay? I'm sure you probably had a general concept of it already, but I think this is an interesting topic. Okay, and so the observed color is predominantly the colors reflected, and depending on which ones are reflected, we may see, a different shade of that color. Okay. Okay, so coming back to this idea of wavelength, just remember the color of electromagnetic radiation is determined by its wavelength. Okay, or in other words, its frequency. Remember those two are sort of interchangeable. Okay, so depending on the wavelength, we may have higher energy blue light or we may have lower energy red light. Okay, but as that changes, so does the color. Okay, the intensity of the light, however, not the color, but the intensity, is based on the amplitude. So remember we said if we have something with a bigger amplitude, okay, we're going to have more light there. It's going to be a brighter light, in other words, compared to something that has a smaller amplitude. Okay, so we can have light that's the same color, but if it has different amplitudes, then it's going to have different intensity. And we have two types of interference. So you may be thinking, okay, well, what happens when two waves of light interact with each other? Because, of course, that could happen. Okay, so we have two types of interference. We have constructive interference and destructive interference. And constructive interference will be when two waves are in phase. In other words, when their wavelengths overlap. Okay, so an example of that would be down here below. So we have two waves. Okay, and what you'll notice is they're perfectly aligned. Okay, my hand is not, those aren't perfectly straight lines, but take my word for it that these two waves are aligned. So when two waves come into contact in this way, they combine. Okay, so this is additive, in other words. So this is additive, or we call it constructive interference. So these two will add together, and ultimately their intensity or their amplitude will grow. If we have the opposite case, where we have the troughs lined up with crests and crests lined up with troughs, okay, then it's actually going to be destructive. So this would be an example of something being out of phase. And essentially will reduce the amplitude, and if they're perfectly disaligned or perfectly out of phase, it will cancel the wave completely, okay, depending on the amplitude of each. And this gives us what we call an interference pattern. And we should have that on the next slide here. Yeah, so we'll get to that in just a second. Okay, and the reason that is what we're about to talk about, so the interference pattern, is due to diffraction. So let's talk about diffraction a little bit first. So diffraction is the spreading of waves around an obstacle. So this occurs when light when a light wave encounters an obstacle or traverses through a slit similar in size to its wavelength. Okay? So if we have light waves coming in this direction, okay, so these lines just represent the wave crests. Okay, so you end up having this sort of cone shape. Okay, so what you end up with is you end up with light going like this. Okay, so I know my drawing is not exactly perfect here, but you end up with something like that, where you have the different waves going through, and it ends up with this cone shape, sort of like the volume icon we're so used to seeing now. Okay, so this would be an example of diffracted waves. Okay, so this is the wave nature, and remember, this is partly due to the positive and negative interferences, or the constructive and destructive interference, mainly from, well, it's from both. To be perfectly honest, it's from both. Okay, so we had some barrier, the light approaches it, okay, as it goes through, it recombines, and intensity grows again, and so you end up with this cone type shape. So that's the wave nature, wave diffraction. What about the particle nature? Okay, so if it's just a particle, okay, once it smashes into this barrier, it just stops and that's it. And only the pieces that went through the hole, or the slit in this case, okay, those will continue going on. Whereas anything that encounters the barrier just stops. Okay, so hopefully you get the idea from this, what waves look like when they encounter small barriers, and what particles look like when they encounter small barriers. So one will form a new wave, and one just smashes into it and stops. Okay, so what this ends up giving us is what we call the two-slit interference, okay, or the two-slit experiment, or double-slit experiment. You've probably heard of this before. Okay, so if we think about this, we have a barrier that has a slit here and a slit here. Okay, then we have a light source, so you have a light bulb here. Okay, and that light is shining on this double slit barrier. So what you end up with, if light was only a wave, or only, so let's say if it's only a particle, the only thing we would see is two bright dots here and essentially here. Again, sorry for my drawing, I know it's not the best. Okay, so if it was only particles, you'd have two bright spots and nothing else. But this is what we observed. So we observed bright spots here, 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 and here. Okay, in other words, what we end up with is sort of this diffraction type pattern. So it says light diffracted through two slits separated by a distance comparable to the wavelength results in an interference pattern. I said diffraction pattern, I meant interference pattern of the diffracted waves. Okay, so we end up with bright spots and dark spots. So we're used to thinking of light as waves, so this is probably not all that surprising. Okay, so we know that, of course, light would behave something like this. Maybe you wouldn't know exactly that it would form an interference pattern, but you would suspect, okay, yeah, so the light's going to go through. No big deal. Okay, this is the wave behavior. Just keep in mind, this is a wave nature, wave behavior. Okay, so the behavior of light is analogous to an ocean wave. It has a wavelength, an amplitude, and associated frequency. Sorry, we just talked about all that stuff. Okay, it can be explained by classical electromagnetic wave theory. In other words, a light wave's energy is directly proportional to its amplitude and wavelength. So what we talked about when we talked about the electromagnetic spectrum. Okay, we said the shorter the wavelength, the more intense. Okay, so higher frequency, shorter wavelength. Okay, so more electrons can be emitted. We'll talk about that in a little bit. Okay, so we'll talk about this last little bit in just a second. Okay, so in classic electromagnetic wave theory, attribute this effect to the light's energy being transferred to the electron. So what they're saying here, an electron can be emitted. They're talking about the photoelectric effect. Okay, so what they're saying is the photoelectric effect is if you shine light on a metallic surface, it can cause electrons to be emitted from the surface. In other words, you have, say, a piece of metal, okay, and you have maybe a light bulb. Okay, don't make fun of my light bulb. Okay, and you have we have some wavelength of light traveling this way. Okay, what's going to happen is if it's intense enough, it will actually cause electrons to come off the surface. So this is called the photoelectric effect. Okay, and if we have a higher energy wave, more electrons can be emitted. So that's what this last section was saying. Okay, so the photoelectric effect led to the understanding of the particle nature of energy. So I just showed you how we might say that, for sure light is a wave. How can we say that? Well, that's what we just talked about. So that interference pattern. Okay, but we also said in the beginning that it has dual nature, that it also behaves as a particle. Well, how can we prove that? Well, this is one way. Okay, so this is some evidence. So if we shine intense light onto the surface of a metal, we can eject some electrons. Okay, so the discovery of the photoelectric effect led to the understanding of the particulate nature of matter, specifically the electron. Okay, it was Einstein that proposed that the light energy was delivered to the atoms in the form of packets called quanta, or in other words, photons. So quanta and photons are similar. Okay, the energy of a photon of light was directly proportional to its frequency, but inversely proportional to its wavelength. Okay, so the proportionality constant is called Planck's constant, and has a value of 6.626 times 10 to the minus 34 joules per second. Make sure you get this one down. Okay, it's one you're going to use a lot. So we're going to say the energy is equal to Planck constant times the frequency. And we know that frequency is equal to c over lambda. So we can say energy is equal to hc over lambda. So make sure you know these guys. Okay, and remember that h is Planck's constant and c is the speed of light in a vacuum, or the velocity of light in a vacuum. Okay, so it says the laser light used to read a CD has a wavelength of 785 nanometers. Determine the energy and frequency at 785 nanometers. Okay, so give this one a try, and then I will go over it with you. Okay, so let's talk about this one. So first thing we want to do, make sure I'm capturing. Okay, the first thing we want to do is just to convert our wavelength. So they gave us a wavelength in nanometers. We want to put that into meters. So again, remember, divide by 1 times 10 to the 9th. Make sure you know how many nanometers are in a meter. That's just going to be handy for you to know. So you don't have to look it up every time. It's just 1 times 10 to the 9th. So in 1 meter, there's 1 times 10 to the 9th nanometers. Okay. And then do that conversion to get to meters. Okay, now we need this equation. So we need, remember, we're trying to get energy and frequency. So the first thing we need is frequency. Okay, so we'll just say frequency is equal to c over lambda. So divide speed of velocity of light in a vacuum, or speed of light in a vacuum, by the wavelength in meters. Okay, that will give you the frequency. And then we can plug that into E is equal to h nu. Okay, so energy is equal to Planck's constant times the frequency. So just plug those numbers in. And you end up with energy, and notice our unit here is in joules. Okay, so joules are our derived unit for energy. Okay. So hopefully you're not finding those to be too tough. Okay, equations are pretty simple. Just make sure that you know which equations you need. Okay, so this sort of summarizes what we've been talking about. So we said an object gains or loses radiant energy by either absorbing or emitting radiant energy. Sorry. So this is quantization of energy. Remember that radiant energy is absorbed or emitted in discrete packets called quanta, and it's proportional directly to its frequency, where energy is equal to h times velocity, where h is Planck's constant, and it's inversely related to wavelength, where a large wavelength has small frequency, has small energy. Light with short wavelength, in other words, large frequency, has high energy. Pretty much just a summary of everything we just talked about. Okay, so here we can talk about something that happens where, what happens if, for instance, an electron gets excited? What do we mean by exciting an electron? Okay, so we have energy on our y scale here, so energy is increasing as you move towards the top of the slide. And then we have these numbers, n equal to 1, n equal to 2, n equal to 3. Okay, so we'll talk exactly about what the n numbers are in just a second. But for now, just understand that as this number increases, it essentially represents getting further away from the atom, from the center of the atom. Okay, so where 1, the lowest number 1, is like our baseline. Okay, so it's our lowest energy. And for this particular example, 3 will be our highest energy. So what can happen is, if an electron absorbs energy, it can become excited. Okay, so it goes from this base level, in other words, ground state is what we call it, and it gets excited up into a higher energy. So maybe this could be light. So maybe it's an H nu. So this is the way light is represented a lot. So just H nu. That just means it's some wavelength or some frequency of light, some energy of light. Okay, and that can excite the electron up to a higher energy level. Now, once it's there, it's unstable. So remember, we put energy in to excite it, and now once it's here, okay, so here's our electron. Once it's here, it's unstable. So what it wants to do is relax. Okay, it wants to relax down into a lower energy, so it'll relax back down, and then of course it could go back down again, and it could also go all the way back down in one step. Okay, so it could go down one step and then stay there. It could go down one step and then go down a second step, or it could jump multiple steps. But what happens when this occurs, so if it takes energy in to excite it, you can imagine that when it relaxes, it gets energy off. And this is what happens. Okay, so light is emitted as the electron falls back to a lower energy level. So as this relaxes, it's going to give energy back off. And that could be visible light, or it could be the light that's not in the visible spectrum. But it's going to give energy off. Okay, so coming back to this idea of the dual slit experiment or double slit experiment. Okay, so here we have a very similar situation. Okay, so we have a barrier. Okay, so we have a barrier with two slits here and here. Okay, and we're essentially going to fire a particle beam at this barrier, and then we have some detector over here. So if electrons behaved only as particles, so remember what we said, if light behaved only as a particle, all the light that smashed into the barrier just stops, and everything that meets the slit goes through and makes bright spots. Okay, so here we have a detector that can detect electrons. Okay, so if we only had particle behavior, you would only see, I know it's a little bit hard to see on this diagram, but hopefully you can still kind of pick up the meaning. So what they're trying to show you is that if it behaved as a particle, you would end up with just these two bright spots, okay, for each slit in the barrier. Okay, so you wouldn't have that diffraction pattern or that interference pattern that we saw before. You would just have two bright spots. So this would be the particle behavior. Okay, but what do we actually see? So if we perform this experiment, what do we see? So what we actually see is an interference pattern, just like we do with light. Okay, so what does this tell us? It tells us that if electrons have only particle behavior, they would act like the previous example. But what do we actually see? Well, we actually see an interference pattern. And this tells us that, oh, they must have some wave character as well. Okay, so if I run this experiment, so double slit experiment with an electron beam, what I end up seeing is a diffraction pattern just exactly like I see with light. Okay, so it means that it's having those wave-like interactions, having constructive and destructive interference to give me an interference pattern. Okay, so what does that mean? It means it's both. Okay, so I have particle behavior and I have wave behavior. I have both at the same time, which doesn't really make a lot of sense, I know. But that's what makes it interesting, I think, because it is what we believe to be true. Okay, so we end up seeing this interference pattern, telling us, no, in fact, it does have a wave character. Okay, so we don't just see two bright spots, we see the interference pattern. So what I'm telling you is that not only does light behave as a wave and as a particle, but in fact, electrons behave in the same way. So remember we said they're very, very similar, almost interchangeable. Okay, so not only do electrons have particle behavior, not only does light have particle behavior, but they both, in fact, have wave behavior. So we have wave behavior coming from electrons as well as light. We also have particle behavior coming from both. Okay, so talking a little bit deeper about this wave behavior of electrons. So we have what's called the Broglie Experiments. So you've maybe heard of the de Broglie wavelength before. Okay, so the de Broglie experiments led to the idea that the particles could have wave-like character. So we can say that wavelength is equal to h over mass times velocity, where the units are meters for wavelength. We have these units for h, in other words, our Planck's constant, kilograms for mass, and meters per second for velocity, or frequency, I should say. Sometimes PowerPoint corrects new's to just v's, so if you see that, just be aware that it's supposed to be a new. Okay, they predicted that the wavelength, so going back to the de Broglie experiments, predicted that the wavelength of a particle is inversely proportional to its momentum. Okay, so in other words, the faster the particle is moving, okay, that's going to have an effect on its wavelength. Okay, what effect will it have? So if I have a faster moving particle, shorter wavelength. Okay, so momentum is equal to mass times velocity, in other words, mv. Or of course, we know that wavelength is equal to h over momentum. Okay. So because electrons are incredibly small, the wave character behavior is significant. Okay, so electron has a mass of 9.28 times 10 to the minus 28 kilograms. So remember we said one of the reasons we observe this with electrons is their size. Well, since they're so tiny, remember what we just say. So if they're smaller, they have smaller velocity, they have bigger wavelength. Okay, so that's exactly what we see here. Okay, so this is proof of the wave nature of the electron came a few years later. The demonstration of the beam of electrons would produce interference pattern as if they were waves. So what we just talked about. So this is our biggest evidence, okay, for this wave behavior of electrons. Okay, so a problem illustrating duality of matter. So why can we not see the wave properties of large objects? And this is sort of a thought experiment, okay? So we have a baseball versus an electron. So a baseball has a mass of about 115 grams, and say it has a velocity of 100 miles per hour. Maybe you have a MLB pitcher throwing it at us, or throwing it somewhere in general. Maybe not at us, that would be bad. Okay, so what would the wavelength be if we had a baseball with 115 grams and a velocity of 100 miles per hour? Well, we'd come up with something like 1.3 times 10 to the minus 25 nanometers. So not meters, but nanometers. 10 to the minus 25 nanometers. Okay, so that's a very, very, very small wavelength. Whereas if we have the electron, where we have a much smaller mass, okay, we have a much faster velocity, okay, we have a wavelength of 0.388 nanometers. Okay, in comparison, this is much, much longer. Okay, so we would be able to maybe to observe the wavelength of an electron, whereas the baseball, even though it has some wave behavior still, it's such a small wavelength that we can't see it, and we don't really have any way of, testing for that or seeing it. Okay, so the experimental work of Einstein, Planck, and de Broglie led to scientists to propose that matter and energy are one and the same. In other words, this is the dual nature of matter. Okay, so that's kind of what we opened the talk with, if you remember. We were talking about how matter and energy are essentially interchangeable. Okay, and again, that's because of this dual nature. Okay, so here they want us to calculate the energy associated with 1 mole of photons of green light. Okay, so 1 mole of photons of green light, it has 555 nanometers for its wavelength. Calculate the energy associated with this. Okay, so let's take a look at the answer. Hopefully you're able to calculate this one. So it says, calculate the energy associated with 1 mole of photons of green light. Okay, so we have 555 nanometers as our wavelength. First thing we want to do, find frequency. You'll find that a lot, that one of the first things we have to do is convert to frequency. And I'm sorry if you can hear the mowers outside. Not a whole lot I can do about that. Okay, so let's just convert wavelength to frequency. Okay, so just using that same equation. Okay, sorry, I paused for a moment because they were getting really, really loud. I thought it might make it terrible to listen to. So first thing we want to do is we want to calculate frequency. This should be a lambda. Or PowerPoint sometimes thinks it knows better than you. And we'll convert things from Greek letters to Roman letters. Anyway, so first convert your wavelength to meters, because we need that for our frequency calculation. Okay, and then this should be, again, a new, PowerPoint. Okay, so your frequency, okay, so just plug into your frequency equation. So C over lambda. Now that we have lambda in meters, easy enough. So our frequency, okay, is equal to 5.4 times 10 to the 14 per seconds. In other words, wave numbers, or 1 over seconds. Okay, now calculate energy. So that's what it asks us for. It asks us to calculate the energy. So E is equal to H times nu. So now we know our frequency. Okay, so our Planck's constant in joules per second times our frequency. Okay, it gives us 3.58 times 10 to the minus 19 joules per photon. Okay, but what do we ask for? We asked for a whole mole. So this part might have tripped you up. You may not have been sure. Well, it says per mole, or for a whole mole. So how to do that? Well, find it for one photon. And then remember, we have Avogadro's number. So there's 6.02 times 10 to the 23rd photons per mole, just like we have. Remember, we can have anything in a mole. We could have cows in a mole. We could have anything. Okay, lamps, posters, anything. Okay, so just convert to put in terms of per mole. Okay, so you have 216 times 10 to the 5th joules per mole. In other words, 216 kilojoules per mole. Okay, and then make a note here that says this is the range of energies that can break bonds. Well, that's true. Okay, so if we have higher intensity, like something like green light or blue light, this can actually break bonds. So one way to remember that things like blue light and green light, it's a way to remember that those are higher in energy. Just remember that if you buy something like a green laser pointer or a blue laser pointer, okay, those are going to be more expensive than just a regular red laser pointer. The reason that is it takes a more sophisticated setup to produce those green or blue lights. It takes more energy output. Okay, so that's why they cost a little bit more. But it's a good way, I think, to remember that those are higher energy colors. Okay, so the spectra and radiant energy. So atoms or molecules can absorb energy. The energy can be released as light energy. So remember we said we can excite an electron and then it can relax and release energy. If this emitted energy is passed through a prism, a pattern of particular wavelengths of light is observed. Okay, so this pattern of line spectra is unique to the material absorbing the radiant light. So what are we saying? We're saying that for each individual, so for an atom or for a particular molecule, if we excite some electrons with energy and then they relax and give off energy, we can look at that light through a prism. It'll break into a pattern, so that rainbow kind of thing. And that depending on what material we have, it will be unique to that material. Okay, we call this an emission spectrum. Okay, so it's not a continuous spectrum like a rainbow, but it actually has very specific lines. In other words, only colors show up. And this can actually be used to identify a chemical substance. Okay, so each chemical substance has its own unique line spectrum. Okay, and remember that we call this an emission spectrum. It's a line spectrum because we'll actually see individual lines. Okay, so why is that? So why don't we just get all of the colors? Why do we get just particular colors? Well, we take a look at this. So again, remember that our n level is our ground state, so n equal to 1, and this goes all the way up to n is equal to infinity. Okay, it increases its energy, and notice they get smaller and closer together as we go up. Okay, so we can excite an electron from our ground state to our excited state. So we go from here to whatever our top energy state is. Okay, and then once it's there, remember it won't be stable. So it's going to want to relax back down. Okay, and it has a couple ways of doing that. So it can either make big jumps. Okay, so big jumps. So it can take a small step from here to here, and then make a big jump, small step from here to here, and make a big jump, something like that. Okay. Well, let me rephrase that. So it would jump, they can make a small jump to here, and then the big jump, or a small jump to here, then make the big jump, small jump to here, and make the big jump. Okay. And that would produce more energy. Why? Because you have, it's a bigger jump, so it's releasing more energy. Okay, so this would be more like your ultraviolet light. Okay, where if it takes smaller jumps or smaller relaxations. Okay, so when we have excitation, putting in higher energy, relaxing, going to lower energy. Okay, so if it takes smaller jumps down, it produces less or smaller, or let's say it this way. So it produces radiation that has less energy. Okay, so this might be our visible wavelengths. Okay, or if it's even smaller, it gives off less energy. Okay, so these will be your infrared. Okay, so this is the same way that, for instance, LED lights work. Okay, so they have lots and lots of these type of relaxations, and you're using the energy from an outlet or a battery or what have you to actually excite the electrons. And then when they relax, they give off light. And a solar panel actually works in the opposite direction. So you use sunlight, okay, to relax or to excite them, and then when they relax back down, okay, then we suck that energy up. So essentially, LEDs and solar panels are the same thing, but backwards. Okay, but what we're talking about here is just excitation and relaxation of electrons. So if you notice, these all have different wavelengths. Okay, so we have a blue line, a green line, and a red line. But we don't have, for instance, we don't have a yellow line. We don't have an orange line, or really a blue line. So we only have certain wavelengths here. Okay, so in other words, we have lines. Okay, this is where our lines come from. Okay, so it might look something like this. So here we have a hydrogen lamp. Okay, where we're using electricity to excite the electrons. We put it through a slit just to narrow it down. Put it through a prism, and if we look at it, so there's actually just little handheld instruments that you can do this with. There's also some sophisticated ones. But what you end up seeing is individual lines for these individual relaxations. So these particular relaxations, so this is the hydrogen relaxation. So you have 1, 2, 3. So we have some blue ones. We have a couple blue ones and a red one. Okay. So, but notice we don't see the entire spectrum. We don't see a continuous rainbow. You see individual lines. Okay, what this essentially does is it gives you a fingerprint for an atom.